So for today, we will be, first of all, wrapping up the discussion on indirect methods. And then we'll be introducing another class of open loop control strategies, which is the one of direct methods. And so specifically, remember that last time we basically were wrapping up the discussion on indirect methods, where kind of bird's eye view, we were saying that indirect methods represents this class of solution methods for optimal control problems, whereby we define and derive some optimality conditions, which we want to solve for generating candidates for optimality. These optimal conditions boil down into two-point boundary value problems, which we have to solve. And so what we did is essentially started to look at computational methods for solving these two-point boundary value problems, whereby we first of all introduced kind of the solve BVP solver in Python, specifically for an abstract two-point boundary value problem. And so today we will be using the same solve BVP, but this time applied to an actual optimal control problem. First of all, so that you can see how this can be done in practice, and then also for you to have a potentially useful template for optimizing or for solving other optimal control problems. But specifically, we were also mentioning how these the solve BVP solvers, and most solvers out there, to be honest, for two-point boundary value problems, assume that we kind of specify the problem in a quote-unquote standard form, where, for example, we were assuming that the final time is given and known, right? And so we know that in general, we have been dealing with optimal control problems where this is not the case. And so there are a number of tricks that have been developed in order to basically reformulate any given structure of our optimal control problem into a form that is then amenable for classical solvers. And so here there is a reference that I definitely advise you to check out. It's a fairly old reference, dates back to the 1980s, but it has kind of all of these collection of reformulation tricks to indeed massage the problem into one that falls under this standard form. And specifically, for today, I wanted to highlight one of the most common kind of settings whereby the standard form does not apply, which is the one of free final time. So again, these solvers usually assume that we have a given final time. How do we reformulate a problem where the final time is actual decision variable that we want to pick in order to be amenable for this? And a usual trick that happens oftentimes in mathematics is the one of that is so-called of time rescaling, where specifically we will be introducing where we model time t as a kind of normalized time tau times tf. Tau here is this kind of rescaled time which we wish to use. And note that kind of by this definition, tau is t over tf. And so tf is something we don't know, but whatever tf is, tau will be defined between 0 and 1. Because at the final time, this will be tf over tf, which is equal to 1. So overall, this object is something that is between 0 and 1. Now, of course, when we do this kind of reformulation, we need to change the time derivatives. And so specifically, the time derivatives over tau by the chain rule will be the derivative over time times the tau times tf over the tau, which is indeed the tau times tf. So essentially, we want to reformulate the problem in one where the final time is known. We do this by rescaling time according to this new rescaled time tau, which is between 0 and 1. So in this rescaled time, final time is known and equal to 1. When we do this reformulation, we need to adjust the time derivatives, which essentially entails multiplying our time derivatives by tf. The other step that is entailed in this trick is then to introduce kind of a dummy state variable r, which corresponds to the final time and has trivial dynamics r dot equals to 0. So r replaces final time, and in order to model this in our two-point boundary value problem, we need to have some associated dynamics with it. But we know that since r replaces tf for us, which is a constant, its dynamics are trivial, and which it essentially boils down to meaning that R is fixed over time. And so this is basically all that there is with this trick. So we do these modifications and replace all instances of TF with R in our formulation. So any questions about this? But there will be an example where we go into the details of this. OK, that's pretty straightforward. And specifically, the example we will use will relate to the kind of specific optimal control problem we were solving a couple of lectures back, where, if you remember, we were trying to control this particle on a line system, where we wanted to move from a position x0 equal to 10 with 0 velocity to a final position of the origin, so xdf equal to 0, also with 0 velocity. And we wanted to optimize this cost functional, which was comprised of two terms, kind of one term kind of weighting the final time, and one term weighting the control effort in our system. And last week, we derived the solution analytically for this, but now let's model it using the computational methods. And specifically notice that here final time is a free variable. And so we will have to implement exactly these tricks and reformulations that we just described. So essentially, what we're doing here is we're modeling this particle on a line system where, as usual, for our solved BVP, we have to describe, first of all, our dynamics, so the ODE, where actually, just to make sure that we're getting this straight, let me quickly restate the solution and the optimality conditions which we derived for this example. So this is, I'll go quite quickly through this because this is what we did last time, but essentially we solved this problem over here. And so if you remember, to solve this, we applied our classical strategy. So we derived the optimality conditions, which entails, first of all, taking our system, which in this case is a second order system, and write it in as a first order system by augmenting with one additional state variable. So x double dot equals u essentially becomes x1 dot equals x2, and x2 dot equals u. Then once we reformulate it as a first order system, we could apply kind of nominally our optimality conditions. So the first thing that we do, as usual, is we formulate the Hamiltonian, which for us is 1/2 EU squared plus the co-state variables transpose our dynamics. So P1, P2 times x2 u, which is equal to 1/2 PU squared plus P1 x2 plus P2 u. So this is our Hamiltonian. And once we have this, we can apply our optimality conditions. And as usual, and let's just write them down. So the first optimality condition essentially represents the dynamics. So where we know that x dot is equal to the partial derivative of the Hamiltonian with respect to the co-states P. And this is exactly our dynamics over here. The second condition entails setting P dot equal to minus the partial derivative of the Hamiltonian with respect to x, where by doing the partial derivative of the Hamiltonian with respect to our two co-state variables, what we get is P1 dot equals 0, and P2 dot equals minus P1. Right, so the first one is the derivative of the Hamiltonian with respect to x1. There is no x1 here. The second one is with respect to x2. So there is negative P1. And then the third optimality condition entails setting the, so essentially imposing that u has to be a stationary point of our Hamiltonian, which essentially means that the derivative of the Hamiltonian with respect to u has to be equal to 0. Which in this case means that Bu plus P2 has to be equal to 0. And so essentially U is minus P2 over B. And so here we can update this as minus P2 over B. Because remember that usually mechanically how we solve this is that we use this third condition to express U as a function of X and P, and then we do the appropriate substitutions in our differential equations. Okay, so these are our conditions. In order to solve these differential equations, as usual, we need boundary conditions. Where we know the kind of the state at our initial and terminal we know the initial and terminal state. So we know that x1 at time 0 is equal to 10. We know that x2 at time 0 is equal to 0. We know that x1 at tf has to be equal to 0. And we know that x2 at tf has to be equal to 0. Right, so we have our 4 boundary conditions. There we have 5 constants of integration that we will have to pinpoint. And so the additional boundary conditions come from our kind of master boundary condition, where this depends on whether the final state or the final times are fixed or free. And so in this case, we are in a case where the final time is free. And so if you remember from the past lectures, this additional boundary condition essentially entails setting the Hamiltonian evaluated at the final time plus the derivative of the terminal cost in the t, also evaluated at the final time, setting this to 0. Now, I won't go through the derivation of these terms because we did this already, but the result of this is the last boundary condition, which boils down to minus P2 squared TF over 2B plus alpha TS has to be equal to 0. Right, and so here we have our system of differential equations, and here are our boundary conditions. Okay, everything here is not new. I just kind of re-derived it so that we can then visually compare what we are implementing in the code. Okay, and so going back to the code, essentially what we have here is first we define our differential equations. So if you see x1 dot is equal to x2, we have x2 dot is equal to negative P2 over B. We then have so P1 dot is equal to 0 and P2 dot is equal to negative P1. And then here we already are using this reformulation trick, which we just derived, whereby we are adding this additional kind of dummy state variable R with trivial dynamics. Specifically, R dot has to be equal to 0. And we are rescaling these dynamics by TF, right, by the time derivative, which we just discussed before. Now, given this, we also have the boundary conditions. Specifically, remember that these are fed to the solver as residuals. So we have x1 has to be equal to 10, x2 has to be equal to 0, x1 also has to be x1 at the final stage has to be equal to 0, x2 at the final time has to be equal to 0, and then we have our last master boundary condition here. Okay, and then so we have all of our ingredients. So we pass to the solve BVP the differential equations. We pass the boundary conditions. We specify an array of times, of discretized times, which now goes from 0 to 1 because we rescaled time to be between 0 and 1, together with an initial guess for our solutions. And if we run this, what we get is that the final time is equal to 4.47, which, if you recall, is exactly what we were getting by the analytical solution. So if you remember, our analytical solution was looking something like 1800 times B over A to the power of 1 over 5, and this is 4.47. So we do get the same solution, and we can also inspect the the state variables x1 and x2. So x1 indeed at time 0 starts at 10, and at the final time reaches 0. And we see also our control of how we get there. Right, so this is essentially, we reformulated this two-boundary value problem into its standard form and solved it through numerical methods. Okay, any questions about this? Pretty straightforward, right? Okay, and so this kind of concludes our discussion on indirect methods. Again, at a high level, we saw how this entails specifying optimality conditions and then passing them through a numerical solver to solve the resulting two-point boundary value problem. Indirect methods are historically how optimal control and the overall field started. And nowadays, I would say direct methods are definitely increasingly more popular because of their ease of use. That said, indirect methods have their strengths. For example, they can ultimately boil down to having an analytical solution for your control, which is ultimately the gold standard, right? If I have an analytical solution, then essentially computing in real time an optimal control entails a forward pass through a function, which is great. Even if we're not able to solve analytically, we might be able to just derive the control structure of our control profile. Remember last time we were looking at like bang-bang control, bang-of-bang control, which is great for interpretability and just overall system design. But again, indeed, the field of robotics is definitely moving towards direct methods. So let's talk a little bit about those. Okay, so usual roadmap, we are always in the open loop part of our roadmap, looking at direct methods. Yes?
Is that also up?
It is. So all the code is up and you're free to play around with it. Yeah. Okay, so direct methods, of course, at a high level, approach to and try to solve the exact same optimal control problem, where we have cost functional, which we wish to optimize. We have some dynamics. We have an initial state and a terminal state, here expressed as having to belong to some manifold M of f, defined as the zero level sets of a function f. And we might have some control constraints. So here, for simplicity, I am assuming that the terminal cost is equal to 0, but it could be trivially added. And we're also assuming that the initial time t0 is equal to 0. But this is mostly for simplicity and for notation. So until now, indeed, we were approaching this problem through indirect methods, where we defined and derived optimality conditions, and then we solved this, as we just saw, through numerical methods, whereby we're essentially solving these two-point boundary value problems. And indirect methods are referred to as optimized and discretized exactly because of this reason. The optimality conditions relate to the optimized part, and the solving for those optimality conditions through numerical solvers relates with the discretized part, because numerical solvers internally are discretizing time anyways. Direct methods are if you want, the reciprocal of indirect methods, and in a way, I would say that direct methods are probably the more natural approach to approaching optimal control problems, if we were to have discussed this a couple of weeks back. Because nominally what we do is we take the optimal control problem in continuous time, we discretize time and turn this into a nonlinear and constrained optimization problem. And then we can just throw this optimization problem to nonlinear solvers and hope to get a solution out of it. And the reason why direct methods are starting to become and are increasingly more used in robotics is because there have been a lot of improvements in the field of nonlinear optimization that is making the solution of this problem feasible also in real time. There are a number of excellent references. Here I'm just listing a couple for you to look at if you're interested. But so transcription and direct methods at a high level can be subdivided between two subcategories of methods. And the way these two families differentiate from each other is based on how we choose to transcribe, that is, discretize and remodel as a discrete optimization problem, the original optimal control problem. And so we have namely state and control parameterization methods, also known as collocation methods, and control parameterization methods, also known as shooting. So at the high level, starting from the latter, so the control parameterization methods, is that we take the optimal control problem in continuous time, and we will be discretizing time and assume that only the controls for us are variables prone to optimization. So from the perspective of the optimizer and the solver, only the control variables will be variables we are optimizing over. The states are computed recursively through the unrolling of the dynamics. On the other hand, state and control parameterization methods, again, taking the perspective of the black box nonlinear solver, will be transcriptions whereby both the states and the controls will be numerical optimization variables we are free to tune, and the solver will be free to tune. The difference is that in this case, so the state and control parameterization methods, dynamics become constraints that link together the control optimization variables and the state optimization variables. Here, this is just a high-level picture, but we will see in detail both of these classes today. Of course, these two families have pros and cons. So as you can probably imagine, we're discussing these control parameterization methods as methods whereby only the control variables become optimization variables. And so these tend to become smaller optimization problems, simply because we have less variables to optimize over. At the same time, in this family here, because we are enforcing, so the states are only recursively computed through the unrolling and propagation of our dynamics, enforcing constraints over states is definitely more challenging. Because if you imagine the other approach where both states and controls are optimization-based variables, we can directly impose state constraints by just introducing a new constraint on an optimization variable. We'll see this more in the next slides, but here just to give you a feel of the pros and cons of different methods. So simply put, I would say if you have complex state constraints that you would like to include in your optimal control problem, then control parameterization methods might be a good approach because they're just simple and you have less optimization variables for your optimizers. On the other hand, if you have complex state constraints that you would like to enforce, then probably state and control parameterization methods are the way to go. Yes? It's a great question because there are definitely hybrid formulations known as multiple shooting methods. I will discuss them in a few. We won't cover them in depth, but I'll definitely give you pointers for those. But yes, so you're hitting on a point where these pros and cons can be mixed and matched through hybrid methods. Yeah. Okay. So let's start from the state and control parameterization method. So at a high level, what we want to do is take our continuous time optimal control problem and turn it into a discrete time nonlinear optimal control problem. Where the way we do this is there are many transcription methods and ways of discretizing time that we could select. But here we tend to use the simpler of these approaches, which is Euler time discretization. So in order to do this step from continuous time to discrete time, what we do is that we select a time discretization, meaning we discretize time from t0 to tn according to some time interval, which we pick. And then for all of our time steps, so t0 through tn, which now are just indices, we assume what is called a zero order hold on our control, namely that the control between Ti and Ti plus 1 is equal to Ui. So we assume that the control is fixed in between a single time interval. So the other thing that we need to do is essentially we use Euler integration to integrate the dynamics. And remember that, so the dynamics x dot of t equals f x u t. Now we can approximate this as x of t plus delta t minus x of t over delta t. And so from this, what we can essentially write is that xt plus delta t is equal to xt plus delta t times f of x u t. Right? And in the slides, I'm calling delta t h. Yes. Yes, definitely. Yeah, here we're just going for the simplest approach, but you could think of more sophisticated ones. Yeah, so at a high level, again, we want to go from continuous time formulation to the discrete time formulation. We do this by discretizing time, so selecting a range of indices that represent our time. We assume a zero order hold on our controls. And approximate our continuous time dynamics in this way. And then the last thing that we have to do is also discretize the cost, which is here represented by this integral. But notice that if we consider the integral between Ti and Ti plus 1 of g x ut in the t, once we are assuming that we have this zero order hold on our controls, then the integral between, so the cost between Ti and Ti plus 1, this is essentially a constant, right? And so we can approximate this as g of x u t times h, right? Because we can take g outside of the integral, and so we know that we just call this basically the integral between a single time step as h. And that's done, basically, right? So, then you could say, why even bother spending, 3 lectures on indirect methods if this is all you have to do to solve optimal control problems? Again, we said indirect methods have their benefits. I would say especially now in the age of LLMs, to be honest. I'm sure we all know that LLMs can do a great job at solving these PMP problems, aside from our homeworks, of course. But the point is that I think through LLMs, there is also this notion where we can definitely accelerate the design and development process in characterizing the optimality conditions, which is arguably one of the cases why people are going for these indirect methods direct methods in the first place, because it's just simpler. Anyways, this is a parenthesis. But so this is basically all that there is to it on the state and control parameterization method. Any questions on this? We'll see an example shortly on how this is implemented in practice. But any questions on, at a high level, what we're doing? Okay, so indeed, let's see this in practice. So let's solve this problem of crossing the river known as Zermelo's problem. You have a version of this also in your P set. And specifically, the setting here is that we want to cross from an origin point to another destination point on the other side of the river. The river has some flow, which is 0 at the two extremes and stronger in the middle. And specifically here we are assuming we have a constant forward velocity v, and the control for us is represented by the angle between the forward velocity and the and the flow. And specifically, we want to reach this task by minimizing the control effort, expressed as the squared of our control variable u. Why does the angle represent a notion of control effort? It's because if you imagine taking the 180 degrees angle with respect to the flow, this is when you're doing maximum effort because you're essentially going exactly against the flow. If it's 0, you're following the flow, and then you have no cost. So this problem essentially models the fact where we want to reach our destination point on the other side of the river while minimizing overall control effort.
Are there any bounds on, I guess, how the force of the going to be, like, for example, like, you would actually go straight back towards the flow, and you actually invincible, like, is that just like, I guess what would be the word? And acceleration bounds are like how far?
Yeah, so here we don't assume we have acceleration, meaning we assume we have a constant velocity v, and we are controlling this angle. And we assume our angle has some bounds, so we have some umax. Yeah. Does this answer your question? Okay, so here we are indeed defining our problem. So we assume that TF is 10. We have our final coordinates, 10 and 5. Here we represent the flow through this lambda function, where ultimately if y is equal to L, so we are at the upper extreme of our river, this is equal to 0. If y is equal to 0, this is also 0. Right? So this basically encodes that at the two borders of the river, the flow is 0, and it is maximum in between. So here we are representing our optimization variables through basically a concatenation in a vector. So our z variable represents all of our x, y, and u's, where x, y is the position that we have on the plane. Right, so this is our river. This will be x, and this will be y, where this point would be L, and this would be M. Okay, and so first of all, we introduce and we define our bounds for our variables. Specifically, the x's have to be between 0 and M, and our y's have to be between 0 and L. And for our controls, we are bounded between negative umax and umax. Right? We define our cost function as the sum of the squares of our u variables multiplied by h according to our discretization. And then we define our constraints, specifically our dynamics on the x variable, such that the states x I plus 1 are equal to xi plus h times our dynamics. Same thing for the y. So y I plus 1 is equal at yi plus our flow dynamics. And then we have the initial and terminal constraints, right? So we basically say that the first variables of both x and y have to be equal to 0 and M or L, respectively. Okay, and so is this clear, how we are basically mapping from the actual formulation to this code? Yeah, so M or L is this point over here, right? So this would be our coordinate ML, and we start from 0, 0. Is the x the... Yeah. Yeah. Yes?
So is your state here z?
In this code, we are basically defining z as the concatenation of x, y, and u.
So I guess my question is like, why are you putting the control in which state?
This is just to handle it. Okay. In code. Yeah. That makes sense. Yes.
In this model, we are completely noiseless, right? The flow is perfectly described, our motion dynamics are perfectly described.
Yes.
If we think about the generalization process and measurement next technically, would you think of solving it the same way, but then solving it at times with some kind of feedback loop approach?
It's a great question. So here we are assuming kind of the full open loop strategy where we assume the dynamics are perfectly known. Of course, the moment in reality, dynamics are never perfectly known. So usually what happens is that your control stack will definitely have a hierarchy of modules. Maybe you would have some open loop planner, which basically produces a rough plan that I would like to follow. But then in real time, when I'm actually deploying, I will probably have a closed loop module, which basically tracks this plan. This closed loop model will then be, tasked with the problem of, say that this is the path that I decide, but in reality, I will be bounced off this path. The closed loop will tend me to steer towards my nominal path.
So all of this logic is fulfilled.
Yes, so this is one way. One way is handling it through closed loop. And I would say that in general, any deployment has a closed loop flavor to it. Of course, you could also do a more sophisticated open loop planning, where maybe I have some notion of the uncertainty, which I can capture through some random noise, random variable w, which might be, maybe assuming it's kind of Gaussian distributed or something of the like, and then come up with more sophisticated planning strategies. Okay, and so we have all of our ingredients. We need an initial guess. And so here we just come up with a pretty nonsensical, I would say, initial guess. So our x's and y's are set to 1 for all the time. And our u is basically 0.5 of the max that we can solve. It doesn't have to be feasible. It's just an initial guess. So if we run this, what we get is this solution over here. So you can see that indeed we go from 0 at time 0 to 10.5, which is how we defined ML, following this sort of trajectory. And this is a visualization of the optimal control profile over time. Now note that in this case, we were essentially assuming that our Umax, so our bounds of our controls, was equal to 1. And if you look a little bit more closely at our control profile, we never really reached the boundary, right? So this bound on our control is basically non-enforcing or non-restrictive. So let's try to rerun this, but now taking a slightly more restrictive Umax, which is 0.75, which if you note is slightly below kind of our current optimal control profile.
Is this the 0.75 now?
Yes, so u for us is the angle, and so we are indeed assuming, yeah. So if we just run this, first of all, it's taking a little bit more time, which is never a good sign, and then we see that it basically produces garbage, right? So we are not even starting from our initial point, we're not reaching our final point, basically lost in the river. And this is also what the optimizer says, right? So we don't reach a final solution. And this is obviously just a specific case, but I want to kind of use this as an example of the fact that in moving from indirect to direct methods, we're basically transitioning a lot of the effort from the formulation of the problem and the optimality conditions to kind of tweaking and making sure that the optimization actually runs successfully. And so this is why direct methods are also much more susceptible to the quality of the initial guess. and all of many other kind of properties that enable it to be well-conditioned. This is because if you think about it from the solver perspective, the solver is basically, it doesn't know we're solving an optimal control problem, right? It just sees a random nonlinear optimization problem and it's trying to do its best. So for example, a classical strategy that people use to generate better initial guesses is to first solve a simplified version of the full problem that we wish to solve. For example, we might be relaxing some constraints or loosening some of the constraints, and then using this intermediate solution as a candidate initial guess for a further kind of iteration of our problem. And so let's do just that. So here, what we're doing is that we first run the same optimization with the Umax equal 1, so the one where we were actually able to solve the problem. And then let's rerun the 0.75 version where we are assuming now, we are using the previous solve as an initial guess for the second solve. And what we get is that now this converges, and it does indeed follow the bounds on the control. Again, many of the discussions here are definitely problem-specific, but this is just a hint of the kind of sophistications that have to come with direct methods. Okay, any yes?
Your like relaxed version gives you a control input that's higher than 0.75 at the beginning, or some state where you're like outside of bounds at the beginning. How would that like play out in your Morphin state?
So actually, if you think about it, this is what was happening here, right? Because the solution with the bounds to 1 was actually breaking the 75 bounds. But the point is that initial guesses don't have to be feasible, right? So it just have to be an initial point in solution space for the optimizer to start iterating from.
Okay.
Does that make sense?
Like the time zero, like the time zero. Or actually, no, never mind. I think I understand.
In general, the initial guess doesn't have to be feasible. So it doesn't really mind. There's no point in it doesn't really affect the optimization if it's feasible or not. Of course, if it's feasible, probably it's also a better initial guess. Yeah. Yes.
Control that's just angle that's just in radians, but what would the unit be on the control effort?
We're assuming it's radians, and then we are the cost for us is just the squared of the radians over time, essentially. Okay, and so yes, so this is basically the transcription for this example Zermelo problem, where we essentially discretized time. This led to discretized dynamics, where we're multiplying the original dynamics with respect to our time discretization h, and the integrals become sums. Now, of course, here, remember, we're looking at these two broad subcategories of direct methods, specifically the states and control parameterization methods. And so notice that here, the optimization variables for our optimization problems are both the states and the controls, right? Where these two are tied together through the dynamics, which essentially become constraints that tie controls and states together. And these are the results that we just saw. Okay, and so moving to the other family of methods, which is the control parameterization methods, I would say that most of the intuition directly applies. The only two differences are like specifically relate with the optimization variables. So now in the control parameterization methods, only the controls UIs will be our variables for optimization. And the dynamics essentially become the mechanism through which we are implicitly encoding our states by recursively computing the dynamics over time, right? So how we will see now in a moment on the same example in code, we will see how this essentially boils down to defining an optimization problem over use, whereby internally we have this inner loop where we are propagating forward our dynamics. And this is also why it's referred to as kind of shooting methods, because you could imagine we are, pictorially doing something where we have an initial state x0, and then the optimization will choose a set of u's, so from u1 to un. And then internally, we'll have this recursive application of our dynamics, which essentially propagates forwards our states. But apart from that, everything else stays the same. We're again assuming a Euler discretization of time. We use Euler integration to basically integrate our dynamics, with this only distinction that now the controls are the only optimization variables. Yes?
Problems in which you use control parameterization method versus the previous one?
Yeah, so in general, I would say that, so note that well before, if we wanted to include some fancy state control, so a state constraint, so a constraint on the x, since x is an explicit optimization variable, we could have just added that constraint. So say x has to be less or equal than 3, we could just add another constraint saying x has to be less or equal than 3. In this other formulation, the states are recursively computed, and so handling states constraints is much more challenging. And so in kind of at a very high level, more generally, I would say that if you have complex state constraints, then I would go for the state and control parameterization. If you don't, then this could be a viable option, for example. Well, in this case, both would be able to handle this. Yeah.
But if you have control constraints, then you can only do step function changes, or you can only continue with that too.
I would say from the perspective of the optimizer, nothing would change here. Yeah. Okay. All right, so this is indeed exactly what we do. So we transcribe through the control parameterization method the continuous time problem into a discrete time problem. So let's see how this works in the code. Yes. Okay, so the definition of the problem is exactly the same as before. So we have the same goal point. We start from the same origin point. We have the same time horizon and final time TF. The dynamics so the flow of the river is exactly the same. And yeah, so note that now we define this dynamics function, which indeed encodes our dynamic. So the fact that the next x will be the previous x plus the flow of the river. We have some bounds on our controls, exactly as we did before. So u has to be between minus umax and umax. But now the crux is in how we define the constraints, right? So note that now the constraints function is only a function of u, because u is the only optimization variable that we have. And so what we do here is we have this inner loop where we are propagating our dynamics forward, where for all of our controls in a candidate solution U, we essentially propagate the dynamics forward, so we get next state, and then we append these constraints to the state at every time. Note that specifically here we're using inequality constraints, whereby in order to encode the equality constraint that the final state has to be equal to ml, we have both the fact that the state has to be less or equal than ml, and that state has to be greater or equal than ml. But you can probably, so given kind of what we're saying here, you can imagine that the sensitivity of this is much greater, right? Because we are basically the optimization variables cannot be independently tweaked and kind of snapped to respect the constraints, but the influence of the controls on the overall trajectory is kind of accounted for kind of through this propagation of the dynamics. Okay, and so so what we have now is that we encode our initial guess, which again is something pretty random in this case, and we have everything to solve our problem. And if we run this now with the Umax equal to 1, so the same case as before, what we get is the exact same solution. So it's still able to solve this successfully. And if we run the problem with Umax equal to 0.75, we get that this method indeed does solve it directly, right? So again, don't abstract general conclusions from this specific run. But in general, I would say that the control parameterization method is less less dependent on the quality of the initial guess. But this is very much case dependent. Yes?
At all whether you use control dependent versus control and state dependent, because you just kind of wrapped up the state into the controls. I guess I'm now confused because people are talking about, oh, it does matter because when you have like state constraints, then it's important to do X, Y, and Z. But in this case, where you kind of have state constraints, depending on how you want to look at it, it didn't matter. So I guess if you can clarify.
Yeah, it's a good question. Now imagine that here, I hope that kind of it's you agree with me when we say that kind of here, this is something that the solver needs to run internally every time it wants to evaluate some constraints, right? So take the kind of the solver perspective on this, right? We have something, we don't know what it is, an optimization problem that we want to solve, and the only knobs we have to solve this problem are our optimization variables. In this formulation, the only knobs that we have are the controls. And to evaluate how any tweak in my knobs affects the feasibility and quality of my solution, here I need to propagate forward all of my dynamics, which is different from the previous transcription where we could turn our knobs were both the states and the controls, and the states and the controls, and we could verify that in a way more directly. And so the moment where we have, in this case, constraints are pretty simple, mostly bounds. But the moment we have more sophisticated state constraints, you can imagine how this becomes much more kind of sensitive to my knobs, which are my controls. Does it make sense, more or less?
So I guess my confusion comes where it seems like as long as it doesn't get too complicated, this one's better because this is not as susceptible to a bad initial guess. So
I don't want you to take this specific statement and generalize it to any possible problem. For this problem, we saw that initialization didn't matter too much. I would say, in general, maybe there is a slight tendency towards initialization being less relevant here, but in general, it's very much problem dependent.
I'm just thinking in terms of like rules of thumb, is it better to use the state and control constraints and do it that way, and then if you know there are really no state constraints, then go this way, or is it better to go this way?
Yeah, if you like, as a rule of thumb, if you have simple or non-state constraints, then maybe you could try this. If you have complex ones, then you might want to go for the other one. Yeah. Yes.
Say this is good because it guarantees the trajectory is like physically feasible because the dynamics are like all the states are propagated forward based on the control.
Yeah, there is some element of that for sure, in the sense that dynamics are implicitly encoding the fact that no matter how I tune my knobs, the state trajectory that I get is feasible. So there is some element of that for sure. Yeah.
Does the benefit of one or the other kind of depend a lot on the constraints?
Yes, I would say it depends a lot on the constraints and in general the problem setting. Yeah. So one thing I said at the beginning is that this parameterization has fewer variables, and so I kind of hinted at the fact that they were just smaller optimization problems. Of course, it is smaller, but I am propagating these dynamics at every time. So trade-offs, yeah. I think there was, yeah.
Since this all depends on kind of like a numerical propagation, how important would you say is like the selection of step size for these types of methods?
Yeah, so it kind of great follow-up from what we were just saying, because this might seem as a smaller optimization problem, but then in this case, since I'm integrating the dynamics forward, then I might have to, in order to kind of solve my problem accurately, I might need to reduce my step size and discretization. And so this would in turn be a bigger optimization problem. So problem depending matter, but it could matter, the discretization. Right? And also not only the time discretization, but also the way I integrate my dynamics, right? Because in the state space, what we're essentially saying is that we have like a piecewise linear state trajectory that we are approximating the continuous time with. And so, you know, the bigger the step size, the more I have kind of chances of maybe violating constraints in between and things like that. Does it answer your question? Yeah. Oh, sorry. Yeah.
Or a more complicated cost function. Those are sci-fi. I don't know if sufficient to be more about what optimizers are using.
Optimizers do matter a lot. Here we were using like the most standard out there, but definitely. Also within the sci-fi kind of ecosystem, there are a number of different optimizers you can choose. But this is also what I meant with, we are kind of shifting mental effort from formulation of the problem and optimality conditions to the solution of a black box optimization problem. And within this kind of umbrella term, what I mean is that also the choice of the optimizer does play a role. Yeah. Okay. All right. So basically, you know, we saw these two families of transcription methods where at a high level, what we want to achieve is exactly the same thing. So we want to go from our continuous time optimal control problem formulation to a discrete time one, which we can solve through black box numerical solvers. We saw the control parameterization methods, which entails using only the controls as optimization variables. And then in this case, the dynamics are essentially used to recursively propagate forward in time my state trajectory. And we saw the state and control parameterization methods, whereby both states and controls are optimization variables. And these two optimization variables are linked through the dynamics, which become constraints that link these two variables together. Of course, here we're just scratching the surface on the types of approaches that can be used. In general, I think, as your colleague was also alluding to, there are definitely hybrids of these two methods. For example, multiple shooting is one that I definitely wanted to mention. So if at a high level, it's clear what we're doing in the control parameterization methods with this shooting of the dynamics forward in time. In multiple shooting, this is basically a hybrid in the sense that rather than propagating forward my dynamics from the initial condition to the final condition, what I'm doing is I'm doing this single shooting on a smaller subset of my time intervals. So you could imagine something where I'm propagating my dynamics forward in time or only for some subset of the time, and then I'm doing this again, and then I'm doing this again. And we introduce optimization variables at these kind of dislocation times. And the dynamics become constraints where I want to tie these two endpoints together. Again, high-level picture, but what I meant here is that there are some hybridizations of these two approaches. Yes?
So be a little bit more specific on state constraints around those joining points. Okay.
In turn, you will get that. Yeah. Of course, you know, depending on how big your single interval is, you might have the same problems. But in general, yes. And of course, also another discussion that came up is that here we were assuming kind of a simple kind of Euler discretization and integration of our dynamics. We could go for more sophisticated approximations, for example, leveraging polynomials, which lead to a kind of Hermite-Simpson collocation schemes and pseudo-spectral methods. And so, this is kind of an entire family of approaches. Okay, any questions before I move on the last topic for today? Okay, great. I mean, I think it's pretty, I hope it's clear kind of the attractiveness that direct methods have, right? Because we had to spend, multiple lectures into deriving these optimality conditions before going into kind of solving them through numerical methods. Here, we're basically defining the formulation, taking that at face value, discretizing it, and throwing it to numerical optimization methods. And so for the last topic for today is sequential convex programming, which is, arguably actually one of my favorite direct methods, whereby the idea of sequential convex programming is that until now, what we're doing is that we're taking the continuous time formulation, discretizing it into a nonlinear optimization problem, and then solving it through nonlinear solvers. Of course, these nonlinear optimization problems might be challenging to solve. And so sequential convex programming essentially defines an iterative strategy to solve this potentially complex nonlinear optimization problem. And the way it does this is that we will be defining, as the name kind of alludes to, a sequence of convex problems which would ultimately and iteratively lead to the solution of the actual nonlinear problem which we care about solving. Why we care about doing this is because you did a recitation last week about convex optimization. Convex optimization is great because we can solve it easily, fast, and we are guaranteed to get the global optimum. And specifically, the way we do this is by essentially introducing a surrogate problem of our original problem that we wish to solve. And this surrogate problem is essentially a version where we are linearizing and convexifying the kind of nonlinear elements in our optimization problem, right? So, and specifically, where the nonlinearities come from are either usually the dynamics or the cost. So the idea of sequential convex programming is to linearize and convexify the dynamics and cost around nominal trajectories, solve this problem, get a new nominal trajectory, reconvexify, relinearize, and keep iterating this until we get a better solution. But let's look at this a little bit more in detail. Any questions on the high-level perspective here? Yes.
How is the state troubleshooting? Is it similar?
The question is, what is the difference between multiple shooting?
Constantly relinearizing and then you're resolving and you're breaking the chunks.
So here we would basically break down. So here we would be doing one optimization solve, and we're breaking down the trajectory over time, essentially. We have these chunks over time. Here, and it'll be clear now because we will go through it, but here we are not chopping kind of time, but we're just solving different surrogate problems over time. So here it's one single solve. Here will be n solves. But here the single solve is a solve of a non-linear program. Here we will be solving recursively convex programs. Does it make sense? Okay, and so the general idea is that we are, so assume that G, so the cost is convex for now, and let x0, u0 be a nominal trajectory for our states and controls. In this slides, the indices represent iteration steps, where remember this is an iterative algorithm. So here 0 would be the initial guess at iteration 0. which will lead to kind of a surrogate problem, which we will solve to get a nominal guess at iteration 1 and keep iterating over that. So let's x0, u0 be a nominal trajectory, or more concretely, so x0 t would essentially be with t between t0 and tf is a full function, right? So we assume we have a nominal state trajectory and a nominal control signal. So the way we want to linearize, so remember what we're doing here is we are taking the nonlinear program and we want to turn it into a convex optimization problem. And we do this by linearizing the nonlinear dynamics. And specifically, we linearize these dynamics around this nominal trajectory. So we do this as usual through Taylor expansion, right? So what we can do, and we know, is that f of x ut can be approximated as f evaluated at the nominal trajectory x0 u0 t plus the Jacobian, the derivative of the function f with respect to x times the difference, so x minus x0, plus the derivative with respect to f of f with respect to u times u minus u0. Plus, here we would have high order terms. Yeah.
In u naught of t, I always thought x naught is like at t naught, but so what is x naught at like a t naught equal to t naught?
So here we are introducing this. So for the coming 2 slides, the indices represent iteration steps because we are introducing this iterative algorithm. So for us, x naught t is a full function at iteration step 0.
It's like the s.
Yes.
Got it. Okay, so that x naught on that slide is not the same x naught.
Which one?
Where you have x of 0 is x naught, but that is not the same x naught that you're writing. And then you have x of tf.
Yes, you're right. It's confusing. Yeah, I will update it.
Okay.
But is it clear what we are?
Yes, yes. I just what's the little split that I got about.
Yeah. Okay, and so here what we did is we basically linearized the dynamics around nominal trajectory. And so basically what we get is that now, G is convex. We have now linear dynamics. And so we basically get a new problem, which is now linear, right? And so what we would do now is we solve this new problem. We will get a nominal, a new candidate nominal trajectory, x1, u1, where again here the indices represent iteration steps. And we would then just repeat this process whereby we would now re-linearize our dynamics around this updated nominal trajectory, solve the linear problem, and iterate until we, for example, stop improving our solution. Of course, in between these steps, we always have to discretize, right? Because we're doing these through direct methods. And so at every time we would be linearizing the dynamics, we now have a linear optimal control problem. To solve this, we discretize it exactly as we did, which boils down into a convex optimization problem. Solve this and keep iterating. So at a high level, sequential convex programming essentially defines this scheme where we're given a nonlinear optimal control problem in continuous time. To solve this, we define this iterative scheme whereby we linearize the dynamics around a nominal trajectory. Initially, this would just be an initial guess. This would then lead us into defining a continuous time, but linear optimal control problem, which we discretize in time which leads to our convex optimization problem, which we can solve reliably, efficiently, and to the global minimum, which leads to having an updated nominal trajectory, and we keep this iterating on this loop, right? Until some termination criteria is reached. Does it make sense, what we're doing? Yeah, so basically what we're exploiting here is the fact that we are given a nominal trajectory. This would be x0. We exploit the fact that we can basically linearize our nonlinear dynamics around this trajectory, meaning we exploit the fact that deviations around this trajectory essentially can be well approximated by some linear dynamics. And we use these linear dynamics to essentially define a linear optimal control problem, whereby this would lead us to maybe an updated guess, say x1 in this case, which essentially is like a minor tweak around our original solution, hopefully in the right direction. And we keep iterating this and refining our solution until we are satisfied with our solution. Yes?
You talk about your update for your new function when you're talking about the update for the new guesses. So U1, U2, 3, 4. Exactly, how is that exactly set per se?
Can you repeat the question?
Yeah, so you're iterating in your function, so which I'm assuming is that function also changing the x, the u, and the, I guess.
Yes, so this is only in state space. We would be doing this also for the controls. Yeah.
This function represents changing everything. It's a function that changes both the state and the control.
Yes, I'm not sure what you mean by function exactly, but what I'm saying here is I was representing the iterative scheme in state space here. These are our dynamics, yes.
Yes, that's a function describing all of your dynamics. And so that is just representing how you are going to be changing the x to the u in each iteration.
Not really. Among iterations, so these are just the dynamics of our system. What we do is we linearize these dynamics in order to get a linear formulation. We solve this linear formulation to get an updated trajectory. So what brings us from x0 to x1 is one step in this solve, right? So we're solving a convex problem, which leads to the next nominal guess. Mm-hmm.
A new path and a new control.
Yes, and then what we do is we would be relinearizing around the updated nominal trajectory and kind of modifying this again to get the next two and so forth. Okay, so now I want to quickly show this in code as well. So, usual problem. What changes here is that now we are linearizing our dynamics. We are not doing this analytically. We're using JAX to linearize our dynamics. So we have this function here, which essentially computes the Jacobians of our dynamics. So these two terms, which are essentially two matrices, right? This would be a matrix A. This would be a matrix B. And once we have and so we define the linearized dynamics as the original dynamics evaluated at the nominal guess, this one here, plus the derivative of f with respect to x times the displacement in x, plus the derivative of f with respect to u times the displacement in u. And so once we have this, we basically define our sequential convex programming iterations. So here we assume we have a maximum number of iterations that is 100. So for each of our iteration steps or loops, we would be defining an optimal control problem, which essentially entails our x's and u's. For now, ignore the s. We have our controls, so we have our cost function, we have our linearized dynamics, we have our initial and terminal conditions, we have our state and control constraints, and we can just solve it. And we see that kind of this leads to the solution of the same problem. Okay, one thing, yes.
At the start, didn't we come up with a nonlinear programming solution to it? Like, I'm confused when you want to use SCP instead of the original method.
So the problem is that the original nonlinear optimization problem might be just very hard to solve. And so SCP is basically a strategy to solve nonlinear optimization problems, which relies kind of in an inner loop on a convex optimization, which is fast and reliable. And so you could see this as a sophisticated way of solving those nonlinear optimization problems, which is quite effective. And I would say most state-of-the-art approaches nowadays use something along these flavors. Yeah. Yes.
How do we know that linearizing the dynamics and then using like convex optimization to solve each sub-problem will get us like closer to, or like get us a better solution?
Yeah, it's a great question. And I would say, so this is also where kind of most state-of-the-art, so what differentiates between a naive implementation of SCP and a state-of-the-art implementation of SCP, so where this difference lies. And this is because so at the overall, high-level picture, kind of SCP describes a scheme where we are given an initial trajectory guess, somehow. We linearize the non-convexities around this nominal guess, as we just saw. Forget this box for now. We discretize it. We solve it through convex optimization. If we're happy, then we're done. If we're not happy, we start again this loop. Again, ignore this box. What I meant difference between naive implementation and a state-of-the-art implementation exactly lies in these two boxes, whereby since we are introducing this surrogate problem, which is on one hand easy to solve because it's convex, but it could introduce some additional problems. And two specifically relevant ones are artificial infeasibility and artificial unboundedness. So since we're introducing a surrogate problem, this surrogate problem might be infeasible, while the overall nonlinear problem might actually be feasible. And the other problem, artificial unboundedness, is that the convex problem might just lead us into a situation where the optimal solution of the convex problem just leads us to minus infinity, for example. And so there are different ways in which one could approach this. So typically, to handle artificial unboundedness, you want to ensure that in solving the individual iterate, you don't diverge too much from your nominal guess. And this is because since we're linearizing the dynamics, this linearization is only accurate in a neighborhood of the nominal trajectory. And so this is where concepts like truss regions are introduced in order to basically massage the convex problem such that we are not moving too much from the original solution. For example, a truss region constraint could be something where I want to stay within a certain distance from my nominal trajectory. And the other topic is the one of artificial infeasibility. And typically this is handled through slack variables. So a slack variable is something where, say we have a constraint that our u has to be smaller than u max. We could add an additional optimization variable s, which allows us to kind of loosen this constraint if needed, but we would be penalizing this in the cost. So like an updated cost could be the original cost plus s squared, for example. Now this is kind of a long detour, but does this kind of go in the direction of what you're asking? Yeah. And so now to conclude, if you're seeing those s variables before, this was indeed the slack variable. So we are introducing this fictitious optimization variable s, which we are adding to our bound constraints u, and in the cost. So we are penalizing the slack variable. And if you look at the results of the optimization, we see how the slack variable indeed kind of decreases over time. Because initially for the optimization, apparently it is helpful to violate some of the constraints. But then since we're penalizing them, this kind of reduces and ultimately goes to 0. Okay, any questions on this? Okay, perfect. And so, yeah, just to wrap up, this is a nice quote from Professor Tedrick at MIT, where essentially says, as you begin to play with these algorithms on your own problems, you might feel like you're on an emotional roller coaster. And this is because, again, as we were hinting at before, we are kind of shifting a lot of the mental effort into tweaking the nonlinear optimization problem such that it gives us a solution in the end. And so I'm sure you will be going on this roller coaster also through your P-sets. And this kind of concludes the open loop portion of our roadmap. And on Monday, we'll be moving towards closed loop methods through dynamic programming. Thank you.